So today we're going to be talking about problem set 5 and alkene reactions. So the first really big thing for kind of alkene reactions are the mechanisms that will be on test 2. And for test 2, we call them the big three mechanisms, which is halogenation, hydration, and solvation. So with all three of those, there's something really important for all of them, and that is that each of them have carbocation intermediates. So this kind of means that there's a step in between forming the final product and when you break the double bond. And so things that come along with carbocation intermediates are you can have shift. So that means if the double bond is on that one prime substituted carbon and a two prime, but there's a three prime beside it, the carbocation can shift over to that as long as it's within one carbon. But if it starts getting really far away, then the shift will not happen. Another thing with carbocation intermediates is that there's no stereochem. So this kind of means that it doesn't matter like the directionality that you add it. So it can be cis or trans, it does not matter in comparison to the other atoms on the like carbon or the molecule as a whole. And then lastly, the formation of the carbocation is the rate determining step or RDS. So this is something really important for the mechanism. It'll ask for you to like label the RDS, label all the steps, show the arrows where the electrons and stuff are moving and stuff like that. So now we're going to go over kind of how the mechanisms look like. And these are kind of things you just have to memorize, practice, 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 because it'll be most likely one of these three that are on the exam for test 2. So first off, we'll start with halogenation. So halogenation can be any halogen. Right here, we're using chlorine. It could be bromine, iodine. It could be any of them. So what happens is first, the double bond is after the hydrogen right there. Those two electrons that are in that area return to the chlorine. And then we're left with this. The double bond is broken. And since we have, in this far here, we have both a 2 prime, so it has two carbons attached to it, and this one has three right here. So we're going to have our carbocation right here. Give that a little plus charge, and then this would gain our hydrogen, but you don't have to necessarily show the addition of the hydrogen, depending on how it's drawn. And so now we have chlorine floating free, very, very negative. We have the positive right here. So this chlorine is going to go and attack right where that is and add on to where the carbocation is. And that's the mechanism for halogenation. It's very simple, very easy. The double bond attacks, creates the more electric chlorine, and then the chlorine adds on. And one thing to make sure that I just forgot, add your lone pairs. That's very important for the test, and Dr. Berg and the TAs may take off if you don't have that. Something similar to halogenation, a little bit less likely to see this, but just going over as an example. So here we have two halogens, but it's going to function the same way as halogenation. When you're looking at them, you look at the electronegativity to decide which one is going to be the more on the more substituted carbon. So in this case, our chlorine has a more negative delta charge, while the iodine has a more positive due to the electronegativity difference. And with that, since the iodine has less, so less is our electrophile, more electrons is our nucleophile. So our chlorine is going to be our nucleophile like it was above. But in this example, iodine is going to function like hydrogen. So I'm not going to draw out the mechanism because it's going to be the exact same as the one above. But the final product for this one would look like this. Our chlorine there once again. This time we have iodine right there instead of the hydrogen. Pretty simple overall, but something that he might put on the problem set and try to trick you up. So just be careful with that. Next, we have hydration. So hydration has a little bit more complex steps to work with. And we have to start with the formation of the hydronium ion. So on its own, water and sulfuric acid are not going to create anything, or they're not going to add to the double bond anywhere. But when you have it drawn out like this, water is going to attack this hydrogen because it has two lone pairs there. It wants that hydrogen, and the bond's going to go back there. This is going to create our hydronium, which is H3O plus, and it will look like this. And then figure out, so we'll have a negative charge, so it'll be HSO4 minus. It's not as important. We're really focused on our hydronium ion here, which is going to be the part that adds the double bond. So if we move down, now we have our hydronium ion, which we can draw in right here. It's going to work the same, so it's going to attack the hydrogen. We're going to return those electrons back to the oxygen, and it's going to give us this. And so here we have 2' and then 1'. And so initially our hydrogen is going to add right here. But something that's special about this one is that it was going to be a shift. So if we add the hydrogen, say like right there, it's fine. But we kind of have this shift kind of happen. So right now we have a carbocation here. But when we shift, it's going to want to go right here. Since that's the more substituted carbon, it's going to be 3'. So we're kind of just going to see the hydrogen off of here, kind of just switching. And it kind of just happens this way. So then we're going to have the hydrogen still there. Don't need to draw it out or anything. But then our now water molecule that we've created since we took a proton off, looks like this, is going to attack into where the carbocation is. And with that, we have it added. So it's O, H, and it's going to be positive currently. And then you can use any convenient base, which can be denoted as B, or in this case, we can choose the water to take off one of those protons and return the electrons back to the oxygen right there. And our final product down here will be and that's what we're left with. And then we regenerated the hydronium ion. Now during all of this, so over here when we form the carbocation, this would be the RDS right here. It's that step that forms the carbocation the first time. Same with up here in halogenation. This first step right here would be the rate determining step. So now moving on to solvation. Solvation and hydration work very similar to one another. So what's going to happen is we'll have this. But instead of water, it looks a little bit different. This is what that right there looks like on our number one. We have just a or right now it's methanol. The solvation is to create an ether. So it's going to grab that proton, do all the same things, and it's going to be O CH3 lone pair, 2 hydrogens, and a positive charge. And then if we go down here, you can use that to start the mechanism. And this one works the exact same way as hydration above. So I'll do this one in blue. So it's going to attack. It's going to attack the hydrogen. It's not going to attack the methyl group. That's a lot more to kind of work with. And it wants to go for the smaller, easier attackable group in this case. So it takes that group. And then in this case, there's no shift because we have it on that 3' carbon right here, forming carbocation. This is the RDS step, or rate determining step once again. And then we're going to redraw this. Now we have, and with that, it returns there. So we have this H, CH3. And at this point, this negative, or not necessarily a negative charge, but these lone pairs are going to attack there, which leaves us with this. We've added the group on, and it's always going to attach with the O. We still have that H and CH3. And then has a positive charge. And so we want to remove that hydrogen so that it returns both lone pairs to the oxygen so that it's a neutral charge and completes the methoxy addition. So we're going to take our group we made earlier, grab that, return that, and then that's the final product there. A little messy, but the point is there. Practice doing this over and over and over again to make sure that you understand everything. So now we're going to move on to some reactions. So overall with reactions, my best tip, honestly, is just to memorize them. They require practice to understand like what they do. You don't need to know the mechanisms for a lot of these, unless they are the same ones that we just did. Um, but you need to know like how they add. Do they retain stereochemistry? Do they prefer the more substituted product or what? It just depends. So to start off, we're going to look at Br2CH2Cl2. So with this, we're going to add a bromine and another bromine. So we're going to get two bromines added from this. It's going to add anti-addition, so that means the groups are going to be opposite directions. So in anti-addition, if you're adding two groups, one will be cis and one will be trans to the remaining molecules on, in this case, the ring or any other type of addition. And then lastly, there is no carbocation intermediate for this one, so there is no shift. So you don't have to worry about like the more substituted carbon moving around or anything. It's just going to be whatever's there is what you're going to work with. So product-wise, this is going to give us, we're going to retain the ring structure. Our methyl group is going to be on a wedge like this, CH3. And then so we have one bromine and the transposition to everything else. And then the other one is going to be cis. It doesn't matter which one is what. You just kind of have to make sure that the groups line up stereochemistry wise and that is one of each. Okay, I'm moving on to Br2H2O. So this is going to add a Br and an alcohol group. And with this one, it's going to add Markovnikov. So if you don't know, Markovnikov just means adding to the more substituted carbon. And in this case, the OH is going to have that priority over the bromine. And it kind of is due to its base strength. So bromine's a very weak base because it's a conjugate base of a really strong acid. But OH is a relatively strong base, so it's going to add in the more substituted position. So going along with that, this also has anti-addition, which is what I mentioned earlier. This means we're going to have cis versus trans. They're not going to be in the same direction. And then lastly, there is no shift once again because there's no carbocation intermediate. So nothing to worry about with the double bond or the carbocation moving or anything like that. So when we go to add our groups, like I was saying, so our more substituted carbon right here, this is our 3 prime, this is our 2 prime. So our alcohol is going to add on to our 3 prime position. So we'll show that with a wedge. And we'll have our methyl group kind of coming off here. And then our bromine, like this. Once again, showing the anti-addition with the wedge and the dash line, showing the cis versus trans. So for our next reaction, we have H2PD1C, and this is a reduction reaction, so it kind of breaks double bonds, just adds hydrogens. It's a pretty simple reaction, but it's important to remember like what it can do. It's very useful for reducing triple bonds as well, later on when we get to that. So with this, we're going to add H and an H. And with this one, since whenever you add this exact same molecules or atoms, Markovnikov or anti-Markovnikov does not matter because they're the same and have no priority over one another. And so with that, this was going to add syn. The syn addition is when the groups are both cis, both trans, in comparison to what's already there. So if we look at our product, we can say that we already have these hydrogens that are on here, but when we add two more, which is the H2, they both are going to add on a wedge. And this is just pretty much the syn addition. And that's all you do for H2 PD1C. Very important though, because on the test, he will try to trick you up or on the problem set as well. So just make sure you pay attention to that. So down here, we have two reactions to add OH. But there's a difference between the two that we'll get into. So for this first one, we did the mechanism for. So we add an OH and an H. That H adds to the least substituted spot and the OH to the most. And then this reaction is Markovnikov, meaning that alcohol, the OH group wants to add to the more substituted carbon. And then lastly, there is shift because we have a carbocation intermediate. So you can have movement of the carbocation, and so always be sure to look out for that. It is very tricky, so always kind of like go through a checklist when you're doing problems like this, being like, okay, is there room for it to move? Are there any more substituted carbons like on the chain or the ring that it could possibly add to before finishing your answer and stuff? So now when we have our product, so technically our H is kind of here. Don't have to write it out. It's assumed that it's there. When you break the double bond, you just add the OH group right there because it's the more substituted spot. Now with BH3THF, THF is our solvent. You don't really have to know like what THF is right now or anything. You just need to memorize like the reagents here and like what they do and like what's different about this one. So start off, we have OH and H still, exactly the same as the one before. But what's different about this one is that it's anti-Markovnikov or anti-Mark for short. So with that, that means that the group, the priority group, in this case being the alcohol, wants to add to the least substituted carbon um, rather than the most, which is the difference between the other reaction that we just did. And with that, there's no carbocation intermediate, so there is no shift for this one. And then it's going to add syn, which means we're going to have two cis things add. And so like another thing with carbocation intermediates for this one over here, when you have a shift, you never really have to worry about like stereochem or syn or anti-addition because it's always things can move around a lot more. So it's not going to have that special addition like this one right here does. So when we're adding our groups, erase this methyl. So we'll draw this methyl in the transposition. With syn addition, we want both of the groups to be add. So up here is our H, and this is the more substituted carbon. This is our 3 prime. And this is our 2 prime down here. In this case, since it's anti-Markovnikov, our alcohol wants to add syn with our H down here on the 2 prime carbon. So definitely just do a lot of practice, a lot of flashcards. Dr. Berg has great resources in the folders. Harper has great flashcard sets like made up. You can literally like either like print them out or write them down yourself, which I recommend, so that you kind of get practice like writing them and seeing them more and more and more. And just like whenever you get time, just practice, 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 because that's the key to success for one for the mechanism part of this test and for the reaction page, which is worth a lot of, I think, 30 points overall. So I'll move on to a couple more reactions that are a little bit different than the ones we have been doing. So this first one appears MCPBA. And so first off, it's syn addition. So it's going to add in the same direction. And we're going to add an O. And so with this one, stereochem is big. So it's going to retain stereochem. So with this first one, there's not really a lot going on. You kind of just draw out the ring. And it pretty much just adds like this. Not much going on there. There's not a lot to like extra to draw. But now if we look at this one right here, so when we have this, we have two groups going down, our two methyl groups, kind of right here in red, going this way. That means we also have hydrogens going up like this. And so when we draw our final product, we'll do it in blue. So it's going to look a little like this. So we're going to have our main thing here, our oxygen, going up like this. We're going to have our H's on the dashes, and then the methyls for the carbon groups on the wedges. And you can flip the dashes and the wedges. It doesn't um, particularly matter as long as you're showing that the groups are different. So the H's are both up or down, and the carbons are both either up or down. You can't have one carbon in this case for this example being up and down because then that messes up the stereochem from the original problem. So just practice this one a lot. This one's not too bad. You're just adding that oxygen like that. Now for ozonolysis, so right here we have the bottom part, our CH3 2S. There's another um, potential reaction that you can see. It's zinc and then like CH3O and something else. I don't remember off the top of my head exactly what it is, but just be on the lookout for that. Make sure you learn both of them on your flashcard because Dr. Burke can give you either one on the test. But this one we just add two O's and two oxygens to there. So I like to think of ozonolysis as like cutting. So it's literally going to go right down the middle and cut it. I can't really draw scissors, but good enough. Um, and so our product literally looks just like this. And it's as simple as that. That's what the product makes. Now we have the same reaction here. So O3, -78 degrees Celsius, and that's the temperature. It's a very cold running reaction. Make sure you include that, and then CH3, 2, and then S. So this one, you can kind of go two different ways. So you can either draw it in the ring, so like this, like this, like this, and then like that, and then like that. So it can look like that. Actually, like that, or you could draw it out in a straight chain. But I would just recommend leaving it kind of in the ring. I'll redraw that to be a little bit better. And that's kind of what the product for that one looks like. So now we can go over a little bit of the problem set and just kind of like go over um, one of the groups that no one has, just for a little extra practice and kind of like show what exactly is going on. So this is group 2. Let's go get group 12. Okay, so now I have group 12 here. And we can just go through the here and like do a little bit more practice. So with this first one, I'm not going to draw the mechanism or anything, but just kind of note that here we have a 1' carbon, here we have 2. So that CH or that Cl group right here is going to want to add to our more substituted carbon. So in this case, our answer is going to be CH3, CH, CH3, the Cl right there. And that other hydrogen from the HCl added to this carbon because it's the least substituted carbon. Pretty simple. Make sure you include your lone pairs. Ta is my takeoff for that and stuff like that. So our next one, we have H2O, H2SO4. So like I was saying earlier, this one is Markovnikov, so it's going to want to add to the more substituted carbon. So we're going to keep our CH3 group, and we're going to look. So here we have a 2'. We have the carbon here and here. Then this one we have 1, 2, and 3. So 3' right there. So when we add our alcohol group, it's going to add right here. Got a little lone pairs right there. And if you remember the notes from earlier, don't have to worry about like the stereochem on this one or anything like that. Now our next one, our Br2CH2Cl2, we do have stereochemistry to worry about because it adds a certain way. So we'll look first at our carbon. So we have a 3 prime and a 2 prime. Like we have been doing, this one, it's gonna want to add two, well, in this case, both, since we have two bromines adding. Um, but it's not gonna matter. We're gonna make sure we add to both. So we're gonna have our ring like this. And in this case, the stereo can matter. So we're gonna have our CH3 going off like this. One of the bromines going up like this, and then the other one on that dash. And the reason it's like this is because it's anti-addition. So it's going to add cis and trans, not um, both cis or both trans to show that difference. And like if you do not include um, the directionality on this one, you will lose points for not showing the wedges and the dashes. So be careful on questions like this. So our next one, we have solvation once again. I'm not going to go through the mechanism or anything. Works the exact same way as we did before. So here we have 3 prime, here we have 1 prime. So um, very obvious what we're going to add to here. 3 prime is a lot better for our group. So you can redraw this as CH3, C, CH3. And this carbon right here is the one that gets the hydrogen. And then this right here, our O, CH3, or our methoxy group. Pretty simple with that one. So we'll come back to this one at the bottom, and we'll go over here and work on these two. So here we have 1 prime, 2 prime, but when we look over in this part of it, we have a carbon with 3 um, groups. So in this case, since it's fully like full of the methyl groups, one of the methyl groups is actually going to jump over, like so like this one might go over to right there and allow us to add to the more substituted carbon. So our final products here, since we have a carbon-cation shift, so shift happens, it's going to be, because if we had that, it'd be CH3, CH plus, and C like that. But what we're going to have is CH3, C, CH3, H, and then C. Now we have nothing here. So this is where our alcohol group is going to go. Should include those lone pairs. Finish off with our 2 other methyl groups. A big part about these is just writing what you have to start with. So making sure your carbons, you have the exact same number of carbons in your product as your reactant, unless you're adding like carbons and stuff, which we don't really do right now. Because you don't want to start adding carbons to the chain, because on the test you'll get marked wrong for that, and for the problem sets, you will also lose points. So here we have the same 6 carbons total. All looks good, and everything like that. So now our next one, we have Br2H2O, and let's see. So with this one, we have carbons here and here. We have 1 prime and 2 prime. And for this one, if we go back to our notes over here, it's Markovnikov, anti-addition, and there's no shift. So even though it has the ability to shift if there's a carbocation intermediate on this one, there is no carbocation because of the reagents that we have here. So no carbo ion, no shift. Just try to remember that when you're doing these types of problems. So we're going to have our alcohol group in the more substituted carbon, because once again, it's a stronger base and that's where it wants to be. We're gonna have CH2, our bromine goes here. We're gonna have CH, OH down, and this is anti-addition. So that's why they're different directions, even though you don't show like the dash or the wedges, you still kind of show it a little bit in this way. And our CH3 groups down here at the end. And that's pretty much all for that one. So now I have MCPBA. So this one, it looks a little bit different when it's drawn out like this and showing like the groups in the atoms. It works the exact same way as before. So big thing is that it's syn addition. So if we write out our C's, so we're gonna write out C, C, over O going up. That's the big part. And then we'll have our H's on dashes, and then our CH3s on wedges. I usually prefer to have the larger groups on the wedges. Just helps me think a little bit better, keep it track of everything. But either way that you want to do it, um, as long as that they are showing like up and down directionality and stuff that align with each other. So our next one right here is one of the ones I was showing earlier. So we're going to look at the difference between the two electronegativities. So if we're looking at electronegativity, chlorine is a stronger negative than bromine. So if we're looking at this, we have right here we have a 2 prime, right here we have a 3 prime. So in this case, our more negative atom is going to add to the 3 prime carbon position. So if we have CH3 and then CH, this is our 2 prime carbon right here, and this is where the bromine adds. And just making sure to include your lone pairs like that. And then we'll go over again. We have a C, CH3, CH3, and this is where our chlorine adds, just like that. So always making sure to look at the atoms themselves and comparing the electronegativity overall to decide which one is going to add where in these types of like double halogen reactions like this. So now for the last one down here at the bottom, we have a question that's going to show two products. So whenever you see something that has the same substitution pattern, so like we have a group here, group there, and the carbons around them. So this carbon right here, 2 prime, and this carbon right here is also 2 prime. So in this case, we're going to have to add it to both positions um, and get two slightly different products. It's impossible to know like exactly which one is more common without like running the reaction and stuff. So Dr. Bergman asks you to draw both if there are two possible ones, especially on a test. This is very common. So our first answer, CH3, C, Cl, CH2, CH2, CH3, like that. Not too bad there. And then our next product we'll do in red. So we'll have CH3 once again, this time CH2, we're adding that hydrogen there instead of the middle carbon. And then we'll have CH, add the chlorine there. That's the other 2 prime position. Make sure to add the lone pairs. Very easy to forget. Obviously, I've forgotten on most of them. But when you're going through the problem set and you're checking over it, make sure to just kind of do the last minute thing. Still there, then CH2, CH3. So that's pretty much it for the reactions overall. This covers a lot of like chapter 6 reactions. I know the ozonolysis one is not on the problem set, but it's a good one to know. We'll probably see it on the test. Um, but overall, making the flashcards, like I said, it's a great way to study these. Coming to office hours, asking for the TAs or Dr. Berg to explain like the reactions and like how they work, and like if they're Markovnikov, if they're anti-addition, syn addition, all super important things to know. So I recommend like coming and asking for help sooner rather than later, since the test is coming up relatively soon. So I hope this video is helpful. And yeah, good luck studying overall.